Hello everyone. Today, let us ask ourselves, is there any application of trigo functions? You have spent the last few lessons drawing sine x and cosine x and the various transformations on them. But are there any application of this graph? The answer is actually staring back at you. What do you notice is the common property of sine x and cosine x? They are showing repeating patterns. If for sine x, this is the repeating pattern. For cosine x, this is the repeating pattern. So, is there anything in nature or in real life which exhibit repeating behavior? Actually, there are a lot. And we call this repeating behavior periodic motion. Periodic motions are motions where there are repeating behavior or repeating patterns. Now, before we proceed deeper into periodic motion, let us look back at our sine graph. Recall, when we learn how to draw sine graph or cosine graph or tangent graph in that matter, our x values are angles and they are in degrees. Now, there are many periodic behavior in nature where the x values are not angles. One example is, there are periodic motions where the x represent time. So, how do we standardize the units for x? One way is not to use degrees, but to use radian, because radian values have no units, and that works well for many situations. So, let us work with the same graph, sine, cosine, and tangent. However, we change all our x values from degree to radian, because radian values work best. So how do we do that? We know the transformation. Pi radian equals to 180 degrees. Therefore, you can straight away replace this 180 degrees by pi. Okay, sorry, there's no ink there. Okay, this is embarrassing. Alright, not 180 but pi. Okay, and 90 degrees, which is half of 180, so pi over 2. And 270, make the transformation, is actually 3 pi over 2, and 360 is actually 2 pi. Okay, so we change all our x values from degrees to radian by this transformation, and it is because radian values are work best for many situations. Now, one famous application that involves periodic motion is the Ferris wheel. Now, look at this beautiful picture of the Ferris wheel. Now, let us see how this person's height above this special horizontal line changes with time. Alright, I choose to measure height from this horizontal line as compared to the ground. Alright, and I am measuring his height. Okay, if he's above, his height will be positive. If he's below this line, his height will be negative. Alright, so let's imagine in the beginning, that is when time is 0, he started from here. So when he is here, his y is 0. So time is 0, y is 0. So it'll be represented by this point. And let's say 1 minute later, he goes from here to the highest point. And let us assume the highest point he can reach is 0.8 meter. So once 1 minute later, he reaches 0.8 meter. So 1 minute later, he reaches 0.8 meter. So it is this point. And 1 minute after that, which means 2 seconds later, he reaches here, okay, at the other side where y is 0. So after 2 seconds, he goes here where his y is 0. So it'll be represented by this. And 1 second after that, which means 3 seconds later, he goes down here. And let's say the lowest height he can reach is also 0.8 meter. So 3 seconds from the beginning, he reaches here. And we define y below the blue line to be negative. So 3 seconds, his y is negative 0.8. So it is something like this. And 1 second after that, which means 4 seconds has passed, he returned back to his original position where y is 0. So 4 seconds from the beginning, his y returns to 0. Okay, and then he continues and continues and continues. Now if I were to join all these points, you will see a sine curve. Okay, so this once again represents periodic behavior, and this is periodic behavior. And this time we are not using angle for the x values, we are using time. Now I assume something for this example. I assume this person is moving around at constant speed. Okay, if he is moving around at constant speed, then his behavior is periodic. If his speed is not constant, for example, he moved fast here, then he moved at another speed, and he moved at another speed, and his speed is irregular all the time, then there is no periodic behavior. Okay, I am assuming he is moving around at constant speed. Now, is there periodic behavior in our homes? Actually, there are plenty. One example is our ceiling fan. Okay, yes, it's too fast, but if you were to observe the motion of one of the blade, it will exhibit a periodic behavior. Another example is the clock. If you were to observe how the angle of swing changes with time, you will see that there is periodic behavior here too. Now, even the light emitted from the light bulb also exhibit a periodic behavior. Now, light, okay, is composed of electric behavior and magnetic behavior, and those behaviors can be represented by a sine curve. Now you may be wondering, why is it always sine curve but not cosine curve? If you recall, sine curve and cosine curve are almost identical. They just differ by 90 degrees or pi over 2 radian. Now let's previously, this person started here. Okay, previously he was here where y is 0, t is 0. Now let's change that. Let's say in the beginning he did not start here, but instead he started here at the highest point, which was 0.8. So in the beginning, time is 0 and he was at position 0.8. So he would be here instead of here from the previous case. Okay, 1 second later he goes down here. So after 1 second he goes here where the y is 0, which is here. And 1 second later, which means 2 seconds have passed, he goes here and the lowest point is negative 0.8. So after 2 seconds he goes to negative 0.8. So 2 seconds, negative 0.8. And 1 second after that, when 3 seconds have passed, he goes here. So when he is here, his y is 0. So after 3 seconds, his y is 0. And 1 second after that, which means After 4 seconds, he returns back to where he started at 0.8. And if you were to join them, then you get a cosine curve. So sine curve and cosine curve are identical. It just depends on where you start.